Good morning, students. Chapter 8, Gravitation. In last lecture, we have discussed about what is gravitational acceleration below the surface of Earth, then what is gravitational intensity, what is gravitational field. Again, what is gravitational field? If you are given any object having some mass, then due to mass it produces some effect around it in some region. Okay, that effect is called gravitational field, and due to that gravitational field, gravitational forces acting on another object. Another such important topic is gravitational potential. Okay, what is gravitational potential? See here, gravitational potential in gravitational field. We will study the same topic in 12th, electrostatic potential in electric field. Okay, so here you have to remember definition of gravitational potential. Okay, what is gravitational potential, how it is defined, how to obtain its equation. Okay, see, first of all, definition. What is gravitational potential? Okay, gravitational potential is defined as it is negative of work done. It is negative of work done by gravitational force in bringing a body of unit mass from infinite distance to given point in gravitational field. In gravitational field is called gravitational potential at that point. Okay, again, it is negative of work done by gravitational force in bringing a body of unit mass from infinite distance to given point in gravitational field is called gravitational potential at that point. Okay, now how to write this thing like this? Gravitational potential is defined as gravitational potential phi is equal to negative of, it is negative of work done in bringing a body of unit mass from infinite distance to given point. Which object? Object having unit mass. Okay, to given point in gravitational field is called gravitational potential at that point. So phi is equal to minus W infinite to R for unit mass. So means if you remember this equation, you can easily derived, or you can easily write this statement. See, it is negative of work done in bringing a body of unit mass from infinite distance to given point in gravitational field. This is called gravitational potential. Okay, clear about this? Okay, so it is definition. Now we have to obtain equation. Okay, what is equation of gravitational potential? But for Earth, we will obtain equation of gravitational potential of Earth. See, here is gravitational potential of Earth. Gravitational potential of Earth. Okay. Here it is. Okay. Let it is x, y, and here it is origin. And at this origin, if we place, yes, here it is Earth. Okay, here it is Earth. Okay. Yes, here it is Earth. So its center at origin. Okay, at center at origin. And now, due to Earth, let we want to find gravitational potential at point P. We want to find gravitational potential at point P, having position vector r and distance r. Clear about this? Okay, what we have to find? We have to find gravitational potential at point P at a distance r, having position vector r due to Earth. So find gravitational potential. Find gravitational potential at point P. At point P, having position vector r due to Earth. Okay, due to Earth, at this point P, we have to find what is gravitational potential. What is gravitational potential? Chalo, what is gravitational potential? It is negative of work done to bring unit mass from infinite distance to given point. Okay, what we will do? See, I am taking infinite distance. Infinite distance means it is outside its field. So suppose it is point which is at infinite distance. Infinite distance. It is point having infinite distance. Okay, so now understand definition. It is negative of work done by gravitational force in bringing a body of unit mass from infinite to given point. Infinite to given point. Infinite to given point. But here I will find its opposite. I will bring a body of unit mass from point P to infinite. From point P to infinite. Why? I will explain. Okay. So here I will bring a body of unit mass from point P to infinite. From point P to infinite. But first of all, what is force acting on object having unit mass, that is m is equal to 1 at this point? We have to find. Okay. At point P, force acting on object of unit mass, that force F is equal. Chalo, how to write force? Earth, what is mass of Earth? It is ma. Okay, so yes, force between Earth and this object. Force between Earth and this object. Magnitude is easy to write, that is G me 1 upon r square. Yes or no? Mass of Earth is me. Mass of this object is 1, that we have to consider. Distance between them r square. Now, direction. Hello, direction. Okay, so see, what is direction? Direction on this object due to Earth, gravitational forces acting, and gravitational forces attractive. Attractive means towards. Attractive means towards. So that force is acting in this direction. Gravitational force is acting in this direction. Means this force is acting in opposite direction of position vector. So here I have to write minus Here I have to write minus r caret. What is the reason of minus r caret? Do you understand? Hello? Okay. So F is equal to, it is minus Gn upon r square, and here it is r caret, and here it is r caret. Any doubt? Okay. Okay, so yes, it is force acting on unit mass. It is force acting on unit mass. Now, this force, see, F is equal to G. G, that is 6.67 into 10 raised to minus 11, constant. Mass of Earth, constant. Distance, R. Initially, yes, this unit mass is at point P, but we have to bring this mass from P to infinite. So P to infinite, P to infinite. So this distance increases. So is this force constant with respect to distance? No. Here force changes with distance. Force changes with distance. Here force changes with distance. Yes, value of this force changes with distance. So for very small displacement, we can consider force nearly constant. How? See, if I am taking very small displacement dr in this direction, very small displacement dr in this direction. Yes, actually in figure it is large there, but actually it is very small. So if for very small displacement we can consider force nearly constant. Why? Because displacement is very small. Okay, so change in distance, it is also very small. Yes or no? Hello? It is r. If I am taking displacement very small, then this r will be almost same. So for very small displacement, we can consider force nearly constant. So as shown in figure, for very small displacement, dr, as shown in figure, for very small displacement dr, work done by gravitational force, dw is equal. What is equation of work done actually? What is equation of work done? Yes, you know what is equation of work done. The work done is equal to, it is F dot dr. It is F dot dr is equal to, chalo, F, here it is minus G me upon r square r caret dot dr means what? Dr, displacement in this direction. Okay, so displacement in this direction, dr how to find? See, any vector means magnitude into unit vector. So I can write this as dr r caret. Why dr r caret? See, its length is dr. Why r caret? Because see, this displacement is in direction of position vector. Yes, displacement is in direction of position vector. Yes or no? Yes, it is. Now, you may ask me one question. Sir, why work done? Because work done is against this gravitational force. See, due to gravitational force, this object move towards Earth. But if we want to move that object away from Earth, obviously we have to do some work. If I drop this chalk, it is attracted towards Earth by itself. But if I want to move chalk away from Earth, then I have to throw, means I have to provide some external force. I have to do some work. I have to do some work. So here, to bring unit mass from point P to infinite distance, we have to do some force, we have to do some work against this gravitational force. Clear? That's why here, as shown in figure, for very small displacement dr, work done by gravitational force dw is equal to F dot dr is equal to this. Now see what happens is equal to minus g constant, ne constant, distance r square constant, dr displacement constant. Okay, yes, r caret dot r caret, r caret dot r caret. Remember, I dot I 1, j dot j 1, k dot k 1. So r caret dot r caret, it is also 1. Reason here it is r caret dot r caret is equal to 1. Okay. Now it is work done only for small displacement this, but we want to bring this unit mass from point P to infinite. So we can divide the whole path between P and infinite like this, in very small displacement, in very small displacement, in very small displacement. Clear? Yes or no? Okay, we can divide the whole path in very small displacements, in very small displacements. Okay, we want to bring unit mass from P to infinite. So we can assume that this whole path is made up of very small displacement. So find work for this displacement, then find work for this displacement, find work for this displacement, work for this, and how to find total work. Okay, work to bring unit mass from P to infinite, from P to infinite, that is W. P, what is P? Its distance is R, so it is R to infinite is equal to integration of W. Because simple, for this displacement work is dW, for this displacement work dW, for this displacement work dW plus dW plus dW plus dW, and for very small displacement we can say, for very small displacement we can say that summation is converted in integration. So W R to infinite is equal to integration dW. Clear about this? So okay, so now how to write this? So the integration dW, we have to write its value. R to infinite is equal to integration dW. Here it is minus GME upon R square dr. GME minus GME constant out of integration. So minus GME constant. It is integration 1 upon R square to dr. And now as we have to bring unit mass from R to infinite, what is limit? R to infinite. What is limit? R to infinite. Okay. Now what is integration 1 upon R square dr? What is integration 1 upon R square dr? Okay, here it is. I will write here in box. I will write here in box. Integration 1 upon R square dr is equal to integration R raised to minus 2 dr is equal to, what is equation of integration? It is R raised to minus 2 plus 1 divided by minus 2 plus 1. So is equal to, here it is R raised to minus 1 divided by minus 1. So I can write it as minus R raised to minus 1, and is equal to, it is minus 1 upon R. So remember, integration 1 upon r square dr is equal to minus 1 upon r. So now we will put directly value here. It is minus gm. What is integration 1 upon r square dr? It is minus 1 upon r. Limit is from r to infinite. Limit is from r to infinite. Easy? Yes or no? Yes. If we bring this minus common, then it is gme. Here it is 1 upon r. Limit is from r to infinite. So is equal to, it is gme. Put limit. R is replaced by upper limit infinite. Minus this r is replaced by, yes, this r is replaced by lower limit. That is 1. Any doubt? Any doubt? Hello? Okay? Sure? Okay, so yes, here it is gme 1 upon infinite minus 1 upon r. So is equal to, it is. So is equal to, it is equal to, it is gme 1 upon infinite will become 0. So it is minus gme upon r. But what is answer of r? It is w r to infinite. It is w r to infinite. W r to infinite is equal to, it is minus gme upon r. Clear about this? Hello? Clear about this? Okay? So yes. How to obtain this equation? Now, we actually have to find gravitational potential, which is phi is equal to minus w infinite to r. Now, here, remember, gravitational field is conservative. And what is meaning of conservation? That you already know from chapter number 6. Yes, we have proved that gravitational field is conservative. Okay, because energy remains constant. And work does not depend on path taken. If work done to bring mass from A to B is 100 joule, then work to bring mass from B to A is minus 100 joule. It is minus 100 joule. So yes, for gravitational field is conservative field. So I can write that W infinite to R is equal to minus W R to infinite. So what is W infinite to R? W infinite to R is equal to minus sign. Yes, minus sign. What is W R to infinite? It is minus gme upon R. So minus will become plus. So therefore W infinite to R is equal to, it is gme upon R. And now what is definition of gravitational potential? Gravitational potential phi is equal to minus W infinite to R. So gravitational potential phi is equal to minus W infinite to R. So phi is equal to minus g me upon R. Phi is equal to minus g me upon R. Phi is equal to, it is minus g me upon R. It is equation. Clear about this? Okay. So yes. Now the conclusion is, due to Earth at a distance r at point P, gravitational potential is minus g me upon R. Simple. Phi is equal to, it is minus g me upon R. G gravitational constant, me mass of Earth, and R is distance. Simple. And as it is negative of work done. This phi is nothing but work done. So it is scalar quantity. Potential is scalar quantity. Clear about this? Okay, how to solve this or how to remember this whole theory? See again. First of all, Earth at point B, take object of unit mass, find force on it. Now, force is acting towards Earth, but you want to move mass from P to infinite, so you have to do work. For work done, we have to divide the whole path in very, very small displacement. For such very small displacement, it is equation of work done. Now, to find total work done between R to infinite, you have to take its integration. And then follow this definition. You can easily derive this equation. Clear about this? Okay, so it is gravitational potential. Yes, we also have to see some special cases for this gravitational potential. See. Okay, now say here, due to Earth at distance r, which is outside, okay, which is outside. This distance, this point B is outside it. Okay, gravitational potential. Gravitational potential due to Earth at a distance r, which is greater than r, because we have considered that object outside. Okay, what is equation? Phi is equal to minus gme upon r. Yes, minus gme upon r. Simple. Okay, if this distance is r, this point is outside. Then what is gravitational potential due to Earth? Gravitational potential due to Earth at distance r, which is greater than re. Phi is equal to minus gme upon r. If we want to find gravitational potential on surface of Earth, gravitational potential on surface of Earth. On surface of Earth means simply you have to bring unit mass from infinite distance to surface of Earth. So you have to put r is equal to re. So it is called phi e. Is equal to, it is minus gme upon r. It is minus gme upon r. Clear? So for Earth means for sphere, for Earth, or I can say for sphere, you have to remember two cases. One, gravitational potential on Earth at distance r, which is greater than re, and on surface. Inside Earth, it is not given in your textbook, so you do not have to remember. Okay, for JEE and NEET part, we will see in lecture of JEE and NEET. Clear? Okay, so yes, in case of Earth, gravitational potential due to Earth at distance r, which is greater than re, and gravitational potential on surface of Earth. Now we are taking one special theory. Okay, the gravitational potential due to hollow spherical shell. Suppose you are given one hollow spherical shell. It is its center. Its mass is m and its radius is r. Its radius is r. Hollow spherical shell means mass is only on its surface. Okay, so for this gravitational hollow spherical shell, we will consider three cases. First, outside. Outside means r greater than r. So for this, gravitational potential phi is equal to minus gm upon r. Simple. It is minus gm upon r. Second, on surface means r is greater than r is equal to r. So phi is equal to, it is minus gm upon r. Okay, and third one inside, and third one inside. Okay, what is inside? So yes, remember this point. Okay, inside spherical shell, gravitational potential at each and every point is same and is equal to potential on surface. Inside, at every point, potential is same. Potential is same and is equal to potential on surface, and is equal to potential on surface. So it is nothing but inside means r less than r. Phi is equal to minus gm upon r. At every point potential is same and is equal to potential on surface, that is phi is equal to minus gm upon r. What is reason? Because inside shell force is equal to 0, so work is also 0. Simply, force is equal to 0, so work is 0. See, what is gravitational potential? It is nothing but work to bring unit mass from infinite distance to given point. But if inside the shell force is 0, means no work done. So it is equal to bring, see, if it is infinite distance, I want to bring mass at this point which is inside. So this total work I can divide in these two parts. This work from infinite distance to one surface means it is nothing but phi is equal to minus gm upon r. Inside there is no force. No force means no work. So work is equal to it is 0. Simple. Okay. So as inside the shell force is 0, no work is done. So therefore potential at each and every point inside the shell is equal to potential on surface. That is why is equal to minus gm upon. Clear? Okay, so this special case you have to remember. In case of solid, right now you have to remember these two cases. We will see different cases in lecture objectively and clear about this. So it is all about gravitational potential. Yes, one last thing for this. Okay, graph of gravitational potential versus distance r. Okay, see, inside means where r is less than r. At each and every point gravitational potential is same and which is equal to surface. So it is constant up to r is equal to r. That is minus gm upon r. Why I have to denote this below the axis? Because it is negative, that's why. Okay, then outside as r increases, this phi, here it is negative sign, so it is increases. Okay, so yes, it is like this. It is like this. Clear? So it is graph of phi, that is gravitational potential versus distance r. In case of hollow spherical shell. In case of hollow spherical shell. Okay, so yes, with this total topic which is gravitational potential is over. Okay.